In this video, we're going to look at the monkey and the coconuts problem, famous old problem, and we're going to use it as as an excuse to sort of play around with Wolfram-Cloud Mathematica. So the inspiration came from a Numberphile video seen here where they talk about the problem. So you have these five guys and a bunch of coconuts and a monkey. And it's also famous enough, it's got its own Wikipedia page. So let's have a quick read. There is a pile of coconuts owned by five men. One man divides the pile into five equal piles, giving one leftover coconut to a passing monkey and takes away his own share. The second man then repeats the procedure, dividing the remaining pile into five and taking away his share, as do the third, fourth, and fifth, each of them finding one coconut left over when dividing the pile by five and giving it to a monkey. Finally, the group divide the remaining coconuts into five equal piles. This time, no coconuts are left over. How many coconuts were there in the original pile? Okay, so I'm going to sort of take the approach, at least some of the approach found in the Numberphile video, sort of write a set of equations, sort of borrow their notation. But I'm going to do three sailors because I don't know, I'm lazy. Okay. So there were in the five-person coconut problem, there are in the end six divisions of the coconuts, each man individually, and then sort of at the end as a group. Okay. So sort of borrowing the notation from the Numberphile video, I'm using C0 to represent the original number of coconuts. And so these variables will all be integers. And again, I'm only going to do three of these sailors. And so the original C0, the original amount of coconuts, is divided by the first division by person number one, sailor number one, divides it into three and has one left over that is given to the monkey. So that you see the one there, you see the 3s1, then that sailor takes that for his share away, and then there is the second division. So in this first line here, I'm going to do a shift enter, and I have div1 equals, and that in Wolfram, in this mathematical language, the sort of single equal is just sort of a naming. So I'm just sort of naming this equation as of the first division. And so there, and then the two equals is the equals of like equation, the equals in an equation, in a standard equation. Okay, so div1 is just the name, and then we have our equation. And then we're going to take two of those piles. One of them is taken away, and then two of those piles, and we're going to repeat the process for the second division. So 2s1 is equal to 1 plus 3s2. So s2 is the number of coconuts that are given on the second division, and there's one for the monkey. So we're entering that. Then we're going to take two of those piles after the second division and do a third division. And so that we're going to have 2s2 equal 1 plus s3. So all these equations, most of these equations look the same, but they just have different coefficient factors, if you will, and different names. So the first division, the second division, the third division, the final division, the group division for me, because I'm only doing three sailors, is that two of the piles left after the third division are divided finally into three, and there was no monkey coconut this last time. Okay. So there we have a set of 4 equations, and I've named them div1, div2, div3, div4. Okay. So some of our Mathematica sort of notation here, 1 equals a sort of a naming. So you can also, you don't need to name things for a given session in Mathematica or Wolfram-Cloud. I could have referenced this equation as either out1 or div1. Sort of nicer when you're communicating with other people to have a name. Like out1 can depend on their history of using the application. And so if I have a name, if we both named it div1, then we are clear what we mean by div1. Whereas, out, the out and the number depends on the history of using the application, which can lead to some confusion sometimes. Okay, so I'm going to solve the second, third, and fourth division. Again, the divisions are just like the names of my equations. I'm going to solve the second division for S1. So I'm going to sort of eliminate the variable S1 down here and then substitute it in here. And so then that first equation will now have C0 and S2. Then I'm going to solve the third division for S2 and substitute it in. And that first equation will be in terms of C and S3. And then I'll do it one last time, solve division 4 for S3 and substitute it in. And then I will get an equation that is just sort of C0 and S4. So solve, substitute, solve, substitute, solve, substitute. I can also like name the solutions. So I'm going to solve the second division, the equation representing the second division, solve it for S1, and then I'm naming that solution S2, the solution to that second equation. And then I am going to substitute, that's what this slash dot is, back into the original division, that original division equation, div1. I'm going to substitute in my solution 2. So here is simplifying. So here's the substitution. I'm doing like 3 things here. So it's a little notationally hairy. I have div1 slash dot sol2. That is me substituting that solution I just found for the second equation in terms of S1. I'm substituting S1 where I find it in div1, the first equation. I am going to simplify that. So this is going to be an equation, a Diophantine equation where I'm interested in integer solutions and I would like integer coefficients, and simplify will do that. So right here in my solution, I have like a half, but it's going to give me sort of all nice integer coefficients when I'm done. And then when I do this substitution, I'll end up with something in curly brackets, and I didn't want to deal, I wanted to get rid of the curly brackets. And so I'm using the double square bracket notation to pick out the one term in here. So that is this game. So that is sort of 3 things piled on top of one another: a substitution, a simplification, and then an extracting. It's in some more complicated structure, and I'm just sort of grabbing the content, which is this square bracket 1. Okay. So that is, I solved division 2 and substituted into division 1, and now I've called it division 1b. It's that top equation, but with a substitution. Now I'm going to solve the third division, the equation for the third division for the S2 variable. And I keep getting the same, results. These are pretty much the same equations, so I get a very similar result each time. But just having Mathematica do the tediousness for me. And then I'm going to, again, simplify. I'm going to substitute in div1 b, what I got above. I'm going to substitute in that solution I just got. I'm going to simplify it. I'm going to grab out of the structure the sort of contents. Okay. One last one. So I solved div1, I solved div2. Sorry, I solved div2, I solved div3, I'm going to solve div4, and I keep substituting always into div1. Okay. So this is the one, there's no monkey in this equation, so we lose the one, but it's this otherwise the same. Solve that, substitute, simplify, grab the one term. Okay, and so here is the equation. The equation obtained in the Numberphile video is of a similar form. The coefficients are much bigger because they're doing 5 and I'm only doing 3. So these numbers end up to be, much larger. Okay. Now, again, we want integer solutions. So this is a linear equation. We just have the variables C0 and S0 only appear, don't have any square terms, so it's a linear equation. And we want and it is a Diophantine equation that we're only really interested in the integer solutions. So I was not very familiar with solving these kind of problems, frankly. And so I looked up some other YouTube videos, and this one was I found nice. I could follow. And you take the Euclid algorithm for finding the greatest common denominator, or divisor, I should say. And then you sort of invert that process. And in this case, it's going to be fairly simple. One thing I want to just jump down and say, now our coefficients are, in this case, the 8 and 81, and this is 2 cubed, and this is what, 3 to the 4th. So it's pretty clear immediately that, there is no common divisor other than 1. But I will, since I do want to show some of the capabilities of Wolfram, then it does have a GCD method. So the GCD of 881, of course, is 1. So, but okay. So that's the GCD is important in these type of equations. So I have two variables and their coefficients, and then I have the constant. And if you take the GCD of the coefficient terms, then if that, in this case, it's a 1, if that is a factor of the constant term, then you have not only a solution, but a whole family of solutions. And if that's not the case, then you have no solutions. Okay. So because the GCD in this case was 1, then of course it's a factor of the constant. And now I just want to show that for people, if you were like me and not as familiar with these kind of equations, here is this idea of the family. So if I take C0 was the one that had a coefficient of 8, but if I add the other coefficient, if if I replace C0 with C0 times the other coefficient, 81 times n, and then I have my 38 and my 81, and then I replace the S4 with, again, S4 plus the other coefficient, 8 times n. And if I, expand that out, then I have 8C0 plus 8 times 81n equals 38 plus 81S4 plus 81 times 8 times n. And I have 8 times 81 times n on both sides. So then that, of course, cancels. And so that is the same equation. So you're sort of led back to the same equation. So you have this way, and n is any then integer, because we are interested in these integer solutions. So if I find a solution, I can find other solutions. Okay. So in this YouTube video, you take the Euclid method for finding a GCD. And in this case, it's sort of like one step and it's done. So this one's particularly easy. So you take the 81 and the 10, the coefficients of the equation, the 81 and the 8, and you say that 81 is 10/8 plus a 1, and I'm already down to 1, and so that 1 then is this GCD. It's not always, it doesn't always go that quickly, but it, did and does in this case. And then, so like in that video, his is not so nice, and so he has to go through several steps to find the GCD, and then he turns all those steps around. For me, it's sort of much easier. So here's the sort of forward Euclid, 81 equals 10 times 8 plus 1. And then we turn this around and say 1 equals 81 times 1 minus 8 times 10. So there are the coefficients, 81 and 8. Then we're going to come in, I don't want a 1, but I want the 38. So 1 is this, that sort of common factor, but the real constant was 38. So sort of come in here and multiply through by a 38. So 38 is 81 times 1 times 38 minus 8 times 10 times 38. Okay. And now I'm just sort of rearranging this to get it in the form of my equation. So the 8, when I write it down, that sort of the 8 was positive. I'm going to take the 81 to the other side. So the 81 was a negative. And then 38 was on its own sides. Okay. So I keep the 38 by itself. I want my 81 in my original equation was negative. So I make this other term, this 38 here, negative. And then I was subtracting 8, but in my original equation, my 8 was positive. So I moved that minus sign sort of into here. So now I have, and then these numbers are a sort of particular solution, a solution. So I have then a solution of minus 380 and minus 38. And again, I'm not using, this is all just one big sort of text thing. I'm telling you how to do it sort of without Wolfram, because I don't really like to use Wolfram. I like it to use it when it's doing something that's tedious and I don't want to do, but I know what to do. I don't like to use it as much when I have no idea what it's doing. So I wanted to sort of convince myself I knew how to do this. Okay, and then I'll show you how to do it in Wolfram, and it will give you the answer in 2 shakes. Okay, but I got this answer of the thing that multiplied the 8 was the C0, and so I got a particular solution of minus 380, and I got the variable that had a coefficient of minus 81 was the S0, and so that was minus 38, and so I have this solution. And then I know then I can add 81 times an integer to C0 and 8 times the same number to S4 and get other solutions. And I'm looking for a solution. I don't want negative 380 coconuts. So I just found out I needed 581s to sort of get myself above zero. And then over here, 5/8. So that was 5/8 was 40 minus 38. That was my 2. And over here, where I got a 25. So I know how to do it. Okay, good for me. Now let's do it in Wolfram. And so it's not, we said this is something that has a lot of solutions. And so we don't want to just, we can't say solve. We have to, Mathematica has a thing called FindInstance. Div1D, Div1 was that first division, and that was the equation I kept as an equation, kept substituting it in. So I had Div1, Div1B, Div1B, C, D. So Div1D is that sort of final equation, my Diophantine, linear Diophantine equation. So I am finding an instance of Div1D, or I could just have used some out number. I'm finding an instance of C0 and S4, and I'm specifying here that I want it to belong to the integers. And smack out without any work, it just happens to be giving me the 25-2 answer that I want, that I like. Okay. I just want to show you some of the other possibilities of FindInstance. To sort of, if it didn't give you the one that you wanted, other things you can do. So you can ask for multiple instances. So I could ask here, I'm adding an argument that's going to say, give me 3 instances. And for some reason, I don't understand what it's doing behind the scenes, but it's sort of all over the place. When I didn't specify and it just gave me 1, it gave me this nice sort of simple 1 close to like the first positive one. Now it's giving me 1 that's very negative, 1 that's fairly negative, 1 that's fairly on the positive side. Okay. So you can play further games with FindInstance. You can sort of do this ampersand, ampersand. You can sort of give some conditions. So now I'm saying find some instances of this Diophantine equation where C0 is greater than 0. So, and I'm saying I want them to be integer, and I want there to be 3 of them. So then it did give me the 25, and then it jumped up into the thousands and the tens of thousands. Again, I don't know what it's doing behind the scenes to come up with these instances, but I can narrow it down a little bit more and say I want answers where C0 falls between 0 and say 200. And that might be too restrictive. I think it is too restrictive if I were sort of doing the 5 Sailor problem or the 3 Sailor problem. This was fine. And again, my main thing is not to solve this problem. It's been solved, but to show you how to work with Wolfram-Cloud. But here I am. I'm finding an instance, infinite number of solutions. I'm finding some of them, just instances of some of them. That was my equation, my Diophantine equation. And here's some condition I'm putting on the instances. I want 0 to be less than C0 to be greater than 0 and less than 200. And those are the 2 things I'm looking for, C0 and S4. I want them to be integer solutions, and I'm looking for 3 solutions. Okay. What if I went over restrictive? What if I said 150? What would it do then? would just give me 2. I asked for 3, it would give me 2 in that case. Go back. Okay, so that's what I wanted to show you here, this famous problem, sort of fun. I'm fun following this Numberphile. I sort of wrote it out as a number of equations, naming the equation, but also putting the equation using solve and substitute. Slash dot is the substitute. I'm using simplify, and I'm grabbing the contents, getting it out of these curly brackets. That's what the square bracket 1 is doing. I sort of solved 3 equations and substituted them in some kind of sequence into the first equation. It got me this Diophantine equation. I sort of found the solution on my own because I didn't want just Mathematica to do all the work. I wanted to understand what was going on and how to solve these things. So I sort of followed a different tutorial, worked that out for myself. But then once I did know how to do it, then I felt comfortable jumping back to Wolfram-Cloud. Sort of in the future, I could say, do it for me. Now, I know in principle how to do it myself. Why don't you do it for me and you do the tedious work? And it knows how to do that. It's not a solve, it's a FindInstance. The equation, variables you're looking for, the sort of specification that you want them to be integer. You can ask for a number of solutions, since you know this thing has a number of solutions, and you can put conditions on the solutions. So if it finds instances meeting those conditions, it will find them for you. Okay, that's what I wanted to do in this video. Thanks for your attention.